Okay. Hello. All right, let's get started with some geo things that you would all probably know, but just as a quick revision. So I think one of the coolest things in geometry when we initially start with is like some things about it related to triangles. Let's try to look at some things related to triangles. So let's start with an arbitrary triangle ABC. Any 3 points which are not collinear. Mm. Okay, let's start with something more simpler. Let's say I give you 2 points. Let's start something very simple. Let's say I give you only 2 points, A and B. Can you draw a circle that passes through them? Yes. Sorry.
Sorry.
Imon, I'm going to mute you. Yes. And how do you do that?
We let AB be the diameter.
Right. So we can just and okay, so like if let's say you're given like a ruler and a compass, then how do you go about doing it? Or like to draw a circle, you need to tell me two things, right? One is like what is the center and what is the and how do you find that center and like what is the radius and how do you find that radius? So what would that be? Yeah, once.
We bisect AB using the compass and
Yeah,
then we place it on the center and draw the circle with the same radius.
right, right. So okay, we that could probably be more rigorous and accurate, but I think the idea seems to be that we look at the midpoint of AB and then take so that these two are equal and take this as the radius. Please excuse my beautiful drawing skills and assume the figures I draw are what I say they are. So it is assume that this is a circle. Okay, is that the only circle possible that passes through A and B?
No, there are many other circles.
Right, and how do we find them? Can we characterize them?
We can draw the perpendicular bisector and
Yeah.
any point on that, if you consider it as a center, then you can draw a circle.
Right. So we know that the certain property about a perpendicular bisector that any point on it is equidistant. In fact, the set of points which are equidistant from A and B is defined as the perpendicular bisector. So any point outside will not be equidistant. Whereas, and exactly the set of points which are equidistant from A and B is exactly the perpendicular bisector. This is something we have probably all seen. And then we can take a point and then just take it as a center and the common distance is the radius to draw all these circles. Okay, this is all easier. Why are we talking about this? All right. Even now, what if I give you 3 points, A, B, and C, and I wanted to draw a circle passing through them?
The intersection of all the perpendicular bisectors of all the three line segments which are being formed.
Okay, so what is that going to be?
The center, the circumcenter.
Okay, so let's consider this perpendicular bisector, and this perpendicular bisector, right? Now, what is going to be the center?
The intersection of all the perpendicular bisectors.
Wait, so like these 3 points?
No, they are going to be concurrent uh, due
Oh,
to a reason.
why? Okay. So somebody, I think, who was saying Anirudh, was it? Yes, I think this like
Yeah,
he's claiming that. Or can you quickly tell us why that is true?
Yeah, if we consider it different, then like if we consider there are 3 points, and if we take one point as x and x such that xb equals xc, and another point, I mean, uh, yeah, there are two perpendicular bisectors of BC and AC intersecting at x. So XB would equal XC
Okay.
and XC would equal A. So XB would equal XA, implying that
Yes.
X is on the perpendicular bisector of AB.
Yes. Exactly. Nice. So just to quickly repeat, okay, this is also something we've probably just seen already. What we do, we know that whatever the center of the circle passing through A, B, and C is, it has to lie on the perpendicular bisector. It has to satisfy this property. Let's say it's O, then it must satisfy OA equals OB equals OC. But that also tells us that it has to lie on the perpendicular bisector of AB, perpendicular bisector of BC, and perpendicular bisector of CA. So we ideally want the three to concur. And that does happen to be true because if you consider X as just the intersection of two perpendicular bisectors, then it turns out that all three of these lines are equal. And this also tells us that the center is unique. So the circle that passes through three, three given points is going to be unique, given that they are non-collinear, of course. Okay. Yeah, that's nice. And there's something more we can there's a lot more things we can do with triangles, right? Let's say now earlier what you were looking at is like you're given 2 points, and what is the set of all points which are equidistant from them? What if I give you two lines and I want you to find the set of all points which are equidistant from the two lines? And by that I mean, so but the distance between a point and a line is the perpendicular distance between. So given two lines L and M, how do we find points which are equidistant from L and M? Do people know what
The
this
angle,
is?
the angle
Yeah,
bisector.
right.
I think
So
it's the
if
angle
you,
bisector.
There will be two angle bisectors. Both of them make the locus.
yes, exactly. So there are going to be two angle bisectors. Um, one is going to be this one is going to be this one. And let's quickly, can somebody, maybe it's not too hard, it's just standard congruence things. Consider any point on this and drop the 90 degrees. Now it's just some RHS or whatever you want to call it. This is the common side. There's a 90-degree angle and the angles are equal. So these two triangles are congruent and this has to be equal to this. Is that okay?
Yeah.
Yeah. And we can do something similar with like on this side as well. So if you have any, in fact, you can make an argument the other way around as well. So if you have any point such that it's equidistant from both of these lines, then it has to lie on the angle bisector, again by RHS. These two triangles will turn out to be congruent, so the angles have to be the same. All right. Okay. So earlier what we did was we looked at the set of all points which are equidistant from 2 points and concluded something about things being concurrent. Now again we can look at let's call it ABC. Now what if I want to find a point which is equidistant from all three sides or all three lines?
It must lie on the angle bisector of the three angles ABC.
Yes. Oh wow, also like I didn't realize Lewish's mic started working. That's amazing.
I connected to different device.
Nice, nice. Okay. So again by like a similar argument as earlier, we can consider the angle bisectors of two of these. And since we know that it's going the angle since this point lies on the angle bisector of AB and BC, we know it's going to be equidistant from these two. And since it lies on the angle bisector of BC and CA, it's going to be equidistant from these two. So all these three are going to be equal. And since these two distances are now equal, it means it lies on the angle bisector of this. So this is called the incenter, and this also gives you the property that three angle bisectors in a triangle are concurrent. All good so far? Please feel free to speak up if something is not okay. In fact, we can do more because as we saw here, the angle bisector, the locus of all the points equidistant from two lines, is not just one angle bisector. In fact, it's both the angle bisectors. So we can actually find some more things. So if I have a triangle, what if I consider these two angle bisectors, these two external angle bisectors instead of the internal ones? Let's say this is BC. Let's call this IA.
Again, it will lie on the angle bisector of A, since
Exactly. Yeah.
the distance of A from AB will be equals to the distance of A from AC, and that implies it lies on the angle bisector.
Yes. So if you again look at these distances, we know that since it lies on this angle bisector, these two lengths are equal. We know that since it lies on this angle bisector, we know that this length is equal to this length. So we know that this first length and the third length must be equal, which tells us that it lies on this angle bisector as well. So in fact, what we have here is the not just that the three internal angle bisectors concur, so the three internal angle bisectors concur, but also that the one internal angle bisector and two external angle bisectors also concurs. Okay, it's not too obvious why this third one. Okay, it is maybe. Okay, maybe something to think about is how do you know that the it's not too hard. How do you know that this point will not lie in the external angle bisector of BSC? Okay, and okay, why is this called the incenter? Does somebody want to quickly say?
It's the
Like,
center
what
of
is it the
the
center of? Yeah,
inscribed
yeah.
circle.
Yes, so if you draw a circle, if you have three equal lengths from a point, then obviously it makes sense to draw a circle. So you draw a circle with center I, and this is radius, and then it turns out that you can make this very neat circle, which is like tangent to all the three sides of the triangle. In fact, you can do something similar over here with IA as the center. This is called the excenter. And you can, if you make this circle, oh my God. We will assume for the purpose of this class that this is a circle. Uh, the circle is also going to be tangent to all the three sides. This is called the AX circle. Okay, please feel free to speak up if there are any questions. Let's try to actually solve some problems now. So Okay. So what are some things? Can we relate the incenter and the excenter? Let's try to look at that. Let's try to make it all in one diagram, right? Okay, please bear with my beautiful drawing skills. All right, so we have this as the incenter. Then we have this as the excenter. This is the A excenter. This is the B excenter. Okay, not bad at all. This is the C excenter. Okay, what are some things you can observe in this figure?
Angle IAIC is equal to 90 degrees.
Yes, that is true. This is going to be 90. And why is that?
With just a bit of angle chasing. I just did this today.
Yes, that's true. So how do we do it? So let's consider this line. This is, let's say this angle is x, this angle is x. Since it's the angle bisector, this angle, if this angle is y, then this angle will also be y, since it's the angle bisector. But we know 2x plus 2y is 180. So x plus y is 90, which means that this angle is going to be 90. That is true.
We can also notice that AI and IA are collinear.
Yes, that's true. AIIA have to be collinear. Similarly,
ABC is
IB is collinear and CIIC is also collinear.
And ABC will be the orthic triangle of IA, IB, IC.
Exactly. So if you consider IA, IB, IC as your main triangle, then as you can see that IAA is just, maybe I'll change this. This is just 90 degrees, which means IAA is
Mama.
the altitude. No, I am not Mama. Okay. Sorry, bad joke. IAA is perpendicular to IBIC, as we can see. So it's the altitude in IAIBIC. Similarly, these two others are also the altitudes. And that gives us a very nice result that tells us that I is something called the orthocenter of IAIBIC. And this triangle is known as the orthic triangle. This in triangle IIBIC. And in fact, if you make IAIBIC your main triangle, then it's also to prove. So if you start with a main triangle, let's just again call it something, and you look at the orthic triangle. So let's call this orthocenter H. These are 90, 90, 90. Then in this, okay, I'll call this DEF. Then in this triangle as well, what can you say? What is H in DEF?
H is the
The
incenter of
incenter
DEF.
of the.
Yes, exactly. So H is going to be the incenter of DEF. And that's not too hard to angle chase and figure out as well. In fact, maybe another nice exercise is to show the existence of H. Again, why do the three altitudes concur always? I think it's also like very cool to just, take a moment and, appreciate that for literally, if you take any triangle whatsoever and you take like any three such lines, it's just like, it's nice to think of it as like some sort of Yeah, when I first saw it, I thought that it was like pretty magical as to why like three seemingly random lines seem to concur. Um, anyways, okay, so we have this. That's quite neat. Let's also try to work with some more circles. So the theme of this class is angle chase, and we will try to stick to that at least. And it's a very broad thing to do, but in general, some nice things to look for when you're angle chasing is what all angles what angles can you compute? Can you compute in maybe let's say the three angles of the triangle or whatever your fixed config is, you fix the angles and what are all the other angles that you can compute. Another nice technique to find new equal angles or find new angles in general is to look for cyclic quadrilaterals or circles. Wait, I can't spell quadrilateral. Yeah, or circles. Anyways, I hope my handwriting is not too bad. So again, some quick, we can just quickly revise some things, but it's angles in a circle are very, very neat. If you have any 4 points A, B, C, D in on a circle. Okay, first of all, we saw that any 3 points, given any 3 points, they lie on a circle. But can you say the same about any 4 points?
No.
Right. And why not?
Because the fourth point,
could be
because
either
we need to
inside or outside.
Yeah, so we already know that for 3 points, the circle has to be unique. We've already concluded that because there's only one possible center. So you can fix 3 of the points and the circle gets fixed. So the fourth point, the so you cannot have any quadrilateral. Any quadrilateral cannot have a circle passing through all 4. It has to be some specific quadrilaterals. So I'll probably just skip through these things, some of these things, because they're done in school. But if you don't know any of them, you can ping me or anybody on the Discord, and we will give you some material to look up. But okay, what angles? What do you know about angles in a cyclic quadrilateral? Uh, just just for the sake of revising it, just for the sake
Opposite
of
angles are
completion.
supplementary.
That is true. So angle ABC and angle CDA add up to 180. And
ABD is equal to ACD.
that is also true. And if you also introduce the center of the circle, let's say, do you know anything about this? Can you say anything more about the angles?
Angle AOD
Is
equal to
isosceles.
isosceles.
AOD is twice ABD.
Yeah, AOD is twice AD. So in general, cyclic quadrilaterals are very nice when it comes to looking at angles. So cyclic quadrilaterals or spotting circles, looking for circles is very, very, very good. Okay, let's try to see some simple things related to circles and triangles and stuff. So let's say you have ABC. Let's say you have the it. Oh no, B should be here. A, B, C. And you can, let's say, make this. Let's. Oh, let me try to make it slightly better. Yeah. This is, guys, this is supposed to be the angle bisector. I is supposed to be somewhere here. IA is supposed to be somewhere here. This is the external angle bisector. The figure is warning. Figure not up to scale, clearly. Okay. Wait, something in the chat? Okay. All right. So what is we already know some things in this, right? We know this is 90, we know this is 90. Can we so can we conclude anything cyclic from
IB,
this?
IA, and C are cyclic.
True. IB, IA, and C is cyclic. And that's because these two are 90 and they add up to an 80. So can we say anything about, yeah?
Also, IIA would be the diameter of that.
And IIA is the diameter. Amazing. With IIA as the diameter. Can we conclude anything about the centers of that
Midpoint of
circle?
III.
It has to be the midpoint of IIA. Now here's a cool fact. This actually lies on
On the
ABC.
circumcircle.
Yes. So does everybody know why it happens? So what I'm claiming is that if you consider this intersection, let me call it MA or something, it is going to be the center of the circle passing through IB, IA, and C.
You can do something like, obviously MA has to be equidistant from B and C. So suppose that at the
Why
point,
is it equidistant from B and C?
no, like if we want to prove that MA is the center of BICIA.
Huh. Yeah, okay, then we want it to be equidistant. Yes.
So assume that like the intersection of the perpendicular bisector of BC with the circle is M, for example.
Okay.
Then
No, let me make a new figure because we're considering some new points. So let's say this point is M. Okay.
then BMC is equal to 180 minus A.
BMC is 180 minus A. Yes. What is it that we want to show? So ideally you want to show that, yeah.
We want to show that MB is equals to MI is equals to MC, and that it is equals to MIA.
Yes.
So we
Also, like the
have that.
first step to showing that is also, is it obvious why MA lies on the angle bisector first of all? Or like why M lies on the angle bisector of BAC?
Yeah, because it's the midpoint of I, so it lies on that angle.
Sure. So in this figure it lies on. So okay. Let's focus on just one figure. Let's say in this figure. So can you first of all show that MAB is equal to MAC?
I mean, yeah, because MABC is MAAC and MACB is
Yes.
MAAB.
Exactly. So MABC, so this angle is equal to this angle. Angle MABC is equal to angle MAAC. And similarly, angle MACB is equal to, guys, what is it behind it? MAAB. But these two are equal by definition because MA lies on the angle bisector. So these two must also be equal, which tells us that this is an isosceles triangle. So now we know that these two are equal. That's a good step.
Now we can prove that
MABI is equal to MABC plus CBI, which is equal to MAAC plus CBI. That's
Yeah,
A by 2
let's call these angles like A by 2, A by 2, B by 2, B by 2, C by 2, C by 2.
So
Then
if
So we
MABI.
keep this as yeah.
if we look at triangle MIC, by some angle chasing, we get that angle MIC is equals to 90 minus B by 2, and we conclude that A by 2 plus
I
C by
think it's
2
also just like yeah, exactly. Exactly. I think a couple of people said the argument. So by exterior, one direct way to look at it is just like the exterior angle theorem in like this triangle. So this angle we already know is going to be A by 2 plus B by 2. But this angle is also A by 2 plus B by 2. Do people see this?
Another interesting thing to look at may be like the perpendicular bisector of BC clearly passes through MA. And since MA lies on IA, and we know that the center of the circle also lies on line IA, which is only one possible intersection. So MA must be the center.
Yes, amazing. That's fair enough. So okay, I'll also get to that. But yes, so by this we get that MAB has and MAI are equal since this triangle is isosceles, and then we get that MA is the center of BIC. And a very good point Nishant also made is that we already know we have already concluded MA lies on the perpendicular bisector of BC. And we know that the center of circle IC IAB must lie it lies on IIA and it lies on perpendicular bisector of BC. And this uniquely defines the center of the circle. And we know that MI satisfies both of those things. So MI has to be the center. So we get that in fact all of these are equal. Is this okay with everyone? Any
Yeah,
questions
clear.
about anything? Maybe I'll actually like I only hear like the same 2-3 voices over and over. So maybe I'll like wait.
Can you repeat again how MAI is equal to MAIA?
Yes. So that's a great question. So are you okay with the fact that MA IA is equal to MABA is equal to MAC? Iman?
Uh, I was telling that repeat that how you concluded the
Yeah.
statement.
Are you are you okay with the fact that MAB is equal to MAC is equal to
Yeah,
MAI?
yeah, I'm okay with it.
And so that tells us that MA is the center of circle BIC, right?
Yeah, right. Okay,
But
okay,
we know that
okay, I got
IA
it.
also lies there. That's one way to look at it. And Nishant also had another way to look at it, but I think this is good enough. Yeah. Any other questions? Anything else you want me to repeat? Okay. All right. Okay, so what else can we do? Let's try to look at the orthic configuration a little bit more, right? Like orthocenters. Maybe not the best angle. Side. Okay. So we have A, B, C, 90, 90, 90. This already gives us a lot of cyclic quadrilaterals and a lot of nice angles. In particular, can somebody tell me what angle BHC is?
90 minus A by 2 or plus.
I don't think that's true.
So
Let's yeah.
We can angle chase it like we know HBC is equals to 90 minus C and HCB is equals to 90
Yes.
minus C. So sum of angles.
Why? AFHE is cyclic, so BHC is equal to EHF, which is 180 minus.
That's another way. Great. So one way, as suggested by I didn't see who suggested it, I think Lavish, was that we can calculate this this is 90. So we know that, and this is C. So this is 90 minus C. And similarly in this is B and this is 90. So this is 90 minus B. Now we can just use angle sum in this and find this. Another way which Rian suggested is you look at this circle, it has to be cyclic. Since this is A, this has to be 180 minus A. So this is also 180 minus A. Right? That's quite neat. And why is that neat? Because now you know that if you have an angle A and if you have somewhere 180 minus A with these two, we know that you'll get a point on the circle. So now we can again introduce the circumcircle and try to do things with H so that you get points on the circumcircle. For example, you have 180 minus A. If you reflect H across D and get this point, let's call it H1, HA. Then this point has to lie on the circumcircle. Do people see why?
Yeah. Because it's some
Yeah.
like BHA, C must be equals to 180 minus A, which implies the
Yeah.
cyclic quadrilateral.
Yeah, exactly. So since we're reflecting H across BC, we get that BHAC is equal to BAC. I mean, BHAC is 180 minus BAC, so it has to lie. You can also do another nice thing where you reflect H, you make this parallelogram instead of a kite. You complete this parallelogram. So, okay, I should not be deleting things ideally, but that's fine for now. You make this parallelogram so that this is parallel to this is parallel to this, and that point, let's call it, let's say, H prime or something, must also lie on that point also must lie on the circle. Do people see why?
Because the angle BHC is same as BHC and that's 180
Yes.
minus A. And in fact, we can say a bit more. AH dash is the diameter.
Yes, AH dash has to be the diameter. If somebody who is not Sanskar or Riyansh or people who have been speaking up, somebody who has not spoken up can maybe help me understand why
Together, H prime BC is 90 minus B because it's a parallelogram, and ABC is B. So AB H prime is 90.
Yeah. Also, just like CH is parallel to H prime B, and CH is perpendicular to AB. So H prime B must also be perpendicular to AB. So that tells you that this angle is 90. And similarly, this angle has to be 90. So H prime is in fact the antipode. Or maybe
H dash
diametrically
is
opposite.
bisected by ABC.
Yes. In fact, since it's a parallelogram, HH dash bisects BC. So this is going to be the midpoint of BC. That's a great observation. Anything else we can observe here?
And in fact, this midpoint is just the circumcenter of BFC and BEC.
Yes, that's also a great observation. So in fact, BFEC are also cyclic, right? Why are BFEC cyclic?
Because
Because angle BFC and angle BEC is 90 degree.
Yes. So they are cyclic and M is the center of the circle. Nice. What else can we observe in this?
Can also get an incenter if H is the incenter of B.
True, H is the incenter of DEF.
Because BFHD is cyclic. So we can get FDH equals FBH, which is FBE, which is equal to FCE. And from that, we can get
Yes,
it equal.
so this angle is equal to this angle, but also this angle is equal to this angle because this bigger circle is cyclic. And then we can look at the smaller circle, which is cyclic, to get that it's equal to this angle. And then we get that DH has to be the angle bisector of FDE. And that's another way to conclude that H is the incenter. There's a lot of cool things actually that you can do in this. For example, if you see some line segment in the middle of a circle, just extend it, because that's usually a very good idea. So this line segment kind of looks sad. It already has one point on the circle. Why not find the other one as well? So we call this point Q. Can you say anything about Q?
What's Q?
Q is obtained by extending H dash H to meet the circle again, the circumcircle of ABC.
HQAE is cyclic. I mean,
HQAEF. Yes. So in
HQAC
fact,
is a rectangle.
HQAC.
H prime, sorry.
Acha, yes, that's true. Because we have that this is a 90 and H prime. Okay, I'll actually just call this A prime. What is this H prime notation? So A prime, these are so that signifies that they are opposites in the circle. So we know that since A and A prime are opposites, A prime is a diameter, this angle is 90. So this is going to be a rectangle. And in fact, we know, so we have angle AQH is 90. But in fact, we also have AEH is 90 and angle AFH is 90. So we get this very nice circle of AQ, FH, and E. In fact, this configuration is very, very, very rich. And why 90? AQH is 90 because angle AQA prime is 90. Because A and A prime are diametrically opposite. And H lies on QA prime. This is a straight line. So that's why this is going to be 90. And that's why we have all of these 5 points lie on the same circle. In fact, this is a very rich configuration that we'll probably study in a separate convex class later, along with some Humpty Dumpty points and stuff. This is actually called the Q point of triangle ABC. I think that's enough exploration in this. Yeah. So I find all of these things very, very cool. Like if you just like pick some random third, fourth grader, be like, see, look at this triangle. I'm going to draw this triangle. Give me any triangle. I'm going to draw a circle. Like there's going to be a unique circle. Then you can tell them, okay, if you look at the orthocenter, look at this three perpendiculars, they're always going to be concurrent. And then look, you can join this point with the midpoint and extend it to get this point, and then you can extend it to get this other point, and then you can draw a circle which passes through 5 of these points, and this is going to be a parallelogram. And I feel like if you like show this to a third grader, it's like no less than a magic trick for them. I find that pretty cool as to how neatly things turn up. Anyways, that's enough about that. Okay. Another just like one side thing I wanted to mention is a cool fact about the orthocenter configuration once again. If you have ABC triangle with H as the orthocenter, can you tell me what the orthocenter of BHC is?
It's A.
A.
Yeah, it's going to be A because you want to drop so if you look at BHC as your main triangle, you drop perpendicular from H to BC, you drop perpendicular from B to HC, and C to BH, and you get that it's A. In fact, the orthocenter of ABH is going to be C by symmetry, and ACH is going to be B. So this set of points A, B, C, H, you take any three, the third point is going to be the orthocenter of the 3 points you take. So this set of 4 points I think is called orthic configuration.
And in fact, their circumradii
It's
would be
quite, yeah, sorry.
huh?
Yes, so that's a good point. The circumradius of
Yeah.
all three of these circles is going to be the same. So this
In fact, what
ABC and BHC.
and their
That's a
like
good observation.
reflection about BC. That's just reflection about BC.
Yes. So if you reflect this circle, so we know that this point over here, if you reflect H across BC, let's say you get H. What did I call it? HA. You can in fact reflect why just H, right? You can reflect this entire thing about BC. You can get this nice config. Let's call this like, what should we call this reflection? So just some names. I'm running out of names. A star. Oh, but this is horrible naming. I'll just call it P. So P is the reflection of A across BC.
A underscore
So
B.
now you get that. There's two things in the underscore. That's too bad. So you get P as this. P is fine, guys. P is not bad for now. So you can get that. We already know that this angle is 180 minus A, and we know that BPC is equal to A. So we get that PBHC is going to be cyclic. And in fact, PBC is like the reflection of ABC across BC. So the circles A, B, C, HA and P, B, C, H are reflections across BC. That is quite neat. And thus they have the same circumradius as well. So BHC and ABC have the same circumradius. That okay?
Yeah.
Any other observations you want to share before we can? Maybe we'll do some 2-3 more cool things. Yeah.
So maybe if we want to create a mirror land, a fun place, so we could just imagine all the sides of the triangles to be mirrors and consider the orthic triangle. So what would happen if we shine a laser across one of the sides, from like say from F to D, then the laser would return back.
Yes, like it would go this way, right? Yeah, it would. That is quite a cool fact. So if you shine a laser from F to D, it will go to E and then come back to F. That's what you mean, right?
Yeah.
That's because H is an incenter.
Yes. That is because the angles are equal. Okay, quite cool. Another nice like concurrency fact I really like. And I was like very blown again when I saw it for the first time. Let's again start with the triangle ABC. And let's give me any 3 points DEF on the 3 sides. Any 3 points at all.
Are you talking
Now
about
I'm going
Miquel?
to. How?
Are you talking about Miquel?
Circles.
don't.
Yeah,
Yes.
yeah.
Yeah.
I found this very cool. If you consider these 3 circles, it turns out that they always intersect at one single point. Damn. Why is this true?
So we'll let the point K to be the
Ah,
intersection of
maybe like I would want to hear from people who have not seen it before. In the meanwhile, you can feel free to try some of the buffer problems. So first of all, to the people who have not seen it before, is the statement clear? Okay, I will
Yes,
assume
clear.
that no question needs it. Okay. Also, sorry, like there's some major glitch with my chat, so I'm not able to follow the most recent chat. Like it won't let me scroll down. So if there's something important in the chat I'm missing, can somebody just unmute and tell me that I'm missing something important in the chat? I would appreciate that. Okay, so how do we even start about proving this? Like usually whenever we want to show some kind of concurrency, like just remember like the first two things that we showed were concurrent. We just considered two of the lines and then showed that the third has to pass through them. So I think that's a good strategy to have while showing concurrency. So let's just consider two circles for now. We will show that the third circle also passes through that intersection point. Right, so let's call these the intersection of these two as K, as someone suggested. Now, what is it that we want to show?
AEKF as concyclic.
Yes, AEKF are concyclic. That's what we want to show. Now, maybe we can take some like 2-3 minutes to think. Wait, I can't spell. Concyclic. Yeah, I can spell. So, how do we show that? What are some angles that we can chase? No, Sanskar, wait. I will pause you. Do you guys all have the buffer problems that were sent?
Yeah, that's what I was saying. People are asking for the buffer problems.
I see. Let me put them in the chat again. Uh, yeah. Okay, so you can't see this chat. Cannot see whether the problems have. I think the problems should have gone by now. All right. Yeah. So how do we show that AEFK are concyclic? We know this is angle B, this is C, this is A. Any ideas?
Give us some hints.
So what are some angles that, so how can you hope to show that AEFK is cyclic? You already know one angle. Can you, what other angles do you think you can compute in this?
Angle
Like for
A,
example,
angle AEK
sorry.
will be equal to angle KDC, and then angle AFK will be equal to BDK. And since these two are supplementary, like BDK and CDK, thus the AFK and AEK will also be 180 degrees. Then they will have a circle.
Yes. Amazing. I like this argument. So first of all, observe that AEK is going to be equal to KDC. Why is that? Because of this cyclicity. We know that these two angles are going to be equal. Similarly, because of this cyclicity, angle KFA is going to be equal to this KDP. And we know that these two marked angles are supplementary because they make a line. So these two are supplementary, so it's a cyclic quadrilateral. Is that okay with everyone?
I don't get the conclusion.
Okay, so do you understand that angle KEA plus angle KFA is 180?
Yeah, I understand it.
So since opposite angles in the triangle in the quadrilateral AEKF are adding up to 180, they're supplementary. So it must be a cyclic quadrilateral.
Okay, I got it.
So all of these three circles pass through the same point K. Quite neat, nice. Yeah, maybe one more standard thing before we move to the problem set. Another similar thing that I find very, very cool. So again, let's go back to the circle. Take any triangle and take any triangle and the unique circumcircle for the triangle. Now take any point that you want on the circumcircle, let's say P. If you drop perpendiculars from P onto the three sides, that is not perpendicular. Yes. So I will drop this perpendicular and this is a bad drawing. I think maybe I will make another one.
I wrote about this in my application form.
Yes, that's amazing. Okay, so we have this. Let's call this D. E. That is very cool. I like this result also. Yeah. So as it turns out, very magically, maybe, so D, E, F are collinears. Damn. So can somebody...
DEF is the Simson line of the triangle ABC.
Yes, so how do we show that they are collinears? It's also called the Simson line. But I forgot the spelling. Is there a P inside this or no?
No,
I don't know.
no.
There is no P. Okay, thank you. Usually you don't trust me with spellings. That is the rule. Okay. Anyway, so how do we show that?
Complete the quadrilateral ABCP. Complete the quadrilateral, please.
Okay.
Now in FPDB, FPDB is cyclic.
FP DB is cyclic. Yes.
Yeah.
Yes. P DB.
So angle FPD is equal to 180 minus angle B.
So angle FPD is 180 minus angle B. Yes. Yes.
Angle APC is 180 minus B.
Yes, that is true.
Then if we subtract angle ABD, then FPA will be equal to DPC.
Yes, so if we subtract this common angle, we will see that this is equal to this. So angle FPA is equal to angle DPC.
And as FPEA is a cyclic quadrilateral, we have FPA, angle FPA is equal to angle FEA, and for similar cyclic quadrilateral DEPC, we have angle DPC is equal to DEC.
Yes, FPA is equal to FEA, so this angle is going to be equal to this angle, and angle DPC is equal to angle DEC because this is cyclic. So the key point is to observe that since there are so many 90 degrees, there are a bunch of cyclic quadrilaterals, and then proceed from there. That's very well done. Basically just chase angles. So now you get that angle FEA is equal to angle DEC. So that must mean that these are all collinear. Okay.
But like there could be other configs also, so I think we should use directed angles here.
That is true. So we could possibly have, like, if you just shift P somewhere else, things could change, and some things could go from 180 minus X to just X. So it's good idea to use directed angles.
Or just
Maybe we'll talk about, yeah.
Or you can
Sorry?
just or you can just tackle each conflict separately.
That is true. You can also just tackle everything separately or just directed angles. There's some material for direct angles also later.
Will you teach
Alright.
directed
I
angles in
think
this
that's-
class?
Okay, so the idea for directed angles is to not is to avoid all of these configuration issues, right? So how do we do that? We use
Taking mod
angles. Yeah.
taking mod 180.
You define first a direction in which you want to take the angle, like conventionally clockwise, and then you take it mod 180.
Yes.
And if you measure it from the other side, you just negate it.
Yes. So the idea is that if you have some things like A, B, C, then you fix some ordering, like Sanskar said, clockwise. Then you see that A, B, C, and so okay. So let me just list down all the rules for this, right? So instead of having this scuffed rule of if this is on the other side, then we will want to have ABC plus ADC is 180. But if it is on the same side, then we will want ABC equal to ADC. And this is basically the idea that is like, stopping us from completing the proof here, because that is what could possibly lead to different things. So we say that in directed angles, you want to define them in such a way that 4 points ABXY lie on a circle, or 4 points ABCD lie on a circle, if and only if ABC, angle ABC is equal to angle ADC. Okay. And so how does this work? Basically, we define angle ABC as this angle, and we define angle ADC like in some way as, so whenever we have two lines, there are two angles to consider, right? One is this one, the other is this one. So we fix some orientation like clockwise, and then we just stick to that and define angles using that. So it's basically that's the idea. I don't want to go too much into it because it might end up confusing people also, but so there are some rules that we follow. For example, we define for any 2 points A and B, we define that the directed angle between the directed angle ABA is always defined to be 0. Then this one rule that Sanskar mentioned, ABC, we always say is negative of angle CBA. If we have, in fact, in a triangle, it turns out that if you add up the 3 triangles in a directed manner, is angle ABC plus angle BCA plus angle CAP, then instead of adding up to 180, we say that direct angles add up to 0. The idea behind that is that this angle and this angle, when we add up, turns out to be this angle, which in some sense is the negative of this angle in the directed angle sense.
Or we could just say that like 180 is 0 in directed angle in this way.
Yes, sure. Fair enough. We are essentially going mod 180 in some way.
Before using directed angles in any contest, how do you prove that directed angle solves all the configuration issues?
Okay. So I think you don't have to prove that in a contest. I think it is directed angles is widely accepted now. You can just use it without proving it in the contest. But you can check out, maybe it's not too hard. I think you can think about it as an exercise as to why it solves the configuration issues.
Okay.
Think about it for a while. We can have a discussion about it later if need. Oh no, sorry. Did I stop screen sharing? Yeah. Can you see the screen?
Not now.
Yeah, now it's
Yeah, now we
Okay.
can.
Okay. All right. I think this is more or less like the things that I want to discuss. Now we can move on to the problems. Let me open the PDF and we can choose one that looks nice enough.
Can we use the Simson line in RMO in type exam without proof?
Yes, Simpson line is well known, so as long as you're stating it, you can use it with that proof.
Like we can use any published theorem in RM or in, for example, like any theorem of PGM you want to use. Stating the properties.
I will not say that you can use any theorem, but you can use almost all theorems. But in general, like try to use theorems which if you know the proof for it, and if you can, recreate it, or if you can like show it, then you can use it probably if it's not too long. Like for example, don't use like Kobayashi or something.
Yeah.
Yes. Okay.
Can you give us a
Let's-
short list of the standard theorems that we can use?
I think like more or less anything that you learned from, like, let's say EGMO by Evan Chen, or anything that we did in today's class is all right to state. If something,
Oh,
if there's something
okay,
that
okay.
requires, if there's something that requires like higher math, or if there's something for which you will need like days to understand just the proof even, then that's probably not something that you are encouraged to use. Okay. Is
Okay.
there, I think we have time to do one or two problems. So I've already shared the PDF with you guys. Is there any particular problem which is like popular and guys want to discuss?
I think
I can't
C5
see the
looks
chat. Can
interesting.
somebody unmute? Okay. A question to debate is the correct pronunciation of EGMO. Is it EGMO or EGMO? Okay. I think I answered it while reading it. But I think I myself like switch between EGMO and EGMO. So I think it's fine. Yeah, P5 looks interesting. What was P5? Okay, so some of these problems I have tried like a very, very long time ago. So I'll probably be solving them again with you guys.
Yeah, we can rediscover the solution.
Oh yeah. Yes. Let me paste the problem. Give me a second. Do you actually want, this looks like a long problem, but it's fine. I think it could be instructive. Okay. So let's all take a few moments to
This looks like
make
Brocard's
a diagram. And no, don't scare me, bro. I had it in my angle choosing list. I don't think I knew Brocard's when I saw this.
You
But
have
like
a
it
lot of
feels like so
midpoints
much.
that's there. Not to draw the diagram with hand.
Sorry, what did Sanskar say?
Someone is warning not to draw the diagram with hand.
We should probably, yeah, or we should like just head solve, huh? No diagrams.
Maybe make 2-3 diagrams and just like make the union of those diagrams seems to be the original.
Fair. They intersect at F. AD and BC intersect. I should have seen this earlier. Okay, it's fine though because we are on OneNote, so we can cheat a little bit. AD and BC intersect at E. K and L are orthogonal projections of F onto AD and BC. Oh my god, what is this wording? Orthogonal projections. K and L. MST are midpoints of EF, CF, DF. EF, CF, DF. So this is M, S, T. It's not too bad of a diagram. So
Just
far.
wait until the circles come. Yeah.
Okay. Prove that the second intersection point of circumcircles of MKT. I see what you're saying.
Right.
Okay.
Perhaps don't draw the circle,
MKT.
just mark the points and just keep in the mind that those 4 points are
Yeah.
No, like, why
That's
don't we
very
draw it?
hard
It
to
actually makes more
do.
sense that way.
MKT and MLS. We
Guys,
don't
I
draw
will
it because
post my
my
diagram on ONC for anyone who wants to look.
is it a handmade diagram or a GeoGebra made diagram?
Handmade, of course.
handmade.
So
Damn.
T is circumcenter of DKF. I think that's visible. S is
We
circumcenter of
just
CLF.
mark the point, I would say, and just encode that, okay, ABCD is cyclic, where D is the mark.
Yeah, let's just mark some point. Okay, first of all, we want to show it some point on CD. I'm actually going to like
Wait, is it
try
the
to go
midpoint
ahead
of
and
CD?
see. Okay, can you? Yes. Okay. So that's an amazing conjecture and intuition. So there seem to be a lot of midpoints. So you think, okay, so it's very good to again conjecture things or wishful thinking as to
In
what
my
would make
diagram,
sense
I
of
had
it going to.
D closer to E than A, and it looks like they intersect at EF, although the diagram is quite sloppy for me. But in mine, you
That
have
would
D
also.
is closer to E, C is closer to E. So all of it is like pouring on EF, intersection CD.
No, but D
Right.
cannot be closer
EF
to A
looks like the
because
rad axis.
AB is smaller than CD.
Yeah, AB is given to be smaller than CD. Yes.
We haven't even looked at power of
Yeah. I don't think this needs. Hopefully, this doesn't need. This wasn't my angle chasing list. We can trust. Let's trust the. I don't know when I made this list, but let's have some trust in the Saee that made this list. If not, we can blame her. It's not on me. Okay.
Should we take a
We have
homothency around
so
F to
what?
make? Oh, sorry.
Yeah. I think we also don't need to do that much. Right? This is a simple angle chase.
Okay, sure.
Sorry. K
Looks
T
simple.
N. You want to show cyclic? Yeah, I don't think this is too hard because we can chase these angles. Can you see how to chase angle MTN?
MTN is just EAC.
MTN is not EAC. Oh,
It's
it is.
EDC. It's EDC, I
Yes.
think. Wait,
No, even
no, it's not.
Miquel would
Our angle
guess
is wrong.
that.
Our angle is
This
wrong.
is fine. So first of all, observe that TN is parallel to AC and TM is parallel to EA. So angle MTN is angle EAC. That is quite neat. Now, can you somehow chase angle?
How is TN parallel to AC again?
By conjecture.
Theorem.
TN is parallel to AC because midpoint theorem. T is the midpoint of this.
Oh, right, yeah.
N is the midpoint of this.
You're working backwards, right?
Yes. So now I'm trying
Oh,
to
okay.
show that MKTN is cyclic.
MTN is equals to EDC, right?
No, why EDC? Or am I tripping? Because TN is parallel to AC, MT is parallel to ED. So, which is like EA. So
No,
it's
that
equal to
point is not
EAC.
A. That's point D. The point A is upside.
This is A, right?
But chasing angle MKN is still not that easy.
Yeah, MKN does not look good.
What do we have to prove here?
We are hoping to show that MKTN is cyclic.
And what's N? Define
N
that
is the midpoint of CD.
as a midpoint of section.
Hmm.
We didn't
Can you make us understand the question first?
Yes.
Wait, what?
So let me repeat the question once again. So you're given cyclic quadrilateral ABCD with F as the intersection of diagonals and E as DA cap CB. Is this fine so far?
Yeah, that's fine.
Right. And then you're considering a bunch of midpoints. So first you drop a perpendicular from F onto AD and BC. So you get points K and L. And you consider midpoints of EF, DF, and CF. Right? And now the objective is to show that you want to show that there is a cyclic quadrilateral that passes through M, the midpoint of EF, and K, which is the perpendicular from F onto A, T, which is the midpoint of FD, and N, which is the midpoint of CD. So what do you want to show? Maybe we can make another diagram. We have this cyclic quadrilateral A, B, C, D.
Wait, you can use
We
the
have
shape option.
this.
I think we can find MKT because you can handle MT. I'll tell.
Why is S there?
Yes.
S is
S? Where is the
yes.
S? Oh, that is not an S. I don't know where it came from. Sorry. I think it is supposed. Oh, it is there, right?
S is the midpoint of CF.
S is the
Yes,
midpoint
so
of CF, yes.
why is it
So
there?
we want to show that those two circles concur.
It's in the problem, Ben.
I mean, in the question, N is not given in the question. I just like gave it away to make the problem easier since it's the first question we are doing. So for now, we
I
just
think we
assume that you
can.
want to show that. Yeah.
I don't understand the prove that line. Prove that the second intersection.
Yeah, we have not proved anything yet. So we are going to prove that if we look at this, what are these named? M, K, T, and M, K, this midpoint is T, this midpoint is N. We are going to show that these are concyclic. That is what our objective is.
We can find
Where
MTK. Like MTK is equal to DKT because MT is parallel to ED.
Yes, you can find this angle.
So DKT is 90 minus half of KTD. Right. Because KT equals TD. Like KFD is a right triangle and T is the midpoint of DF. So T is the circumcenter of KFD.
Yes.
So
So yes, so this angle, so you're finding MTK. So in fact, angle MTK is going to be equal to angle MTF, right?
I did not get that.
So what we have is something that looks like this. This is 90, and this is the midline. So in fact, since this is 90, this is going to be the center. So these are going to be equal. And similarly, these are going to be equal.
Can you label this diagram as well a bit?
Yes, sorry. Let us label this F D E. F D E. The midline is MT and K. MT and K. So first of all, this is 90. So we know that. So first, this is a nice exercise. So that triangle MFT is congruent to triangle MPF. And that gives us that angle MTK has to be equal to angle MTF.
So we know that T is the midpoint of DF. So T is the circumcenter of DKF. So we know that TK is equals to
Yes.
TF.
Yes. And similarly, MK was equal to MF.
Yeah.
So by
Yeah.
SSS, we get that result. And like an easier way to think about it is if you have some triangle and you have the midline, then if you reflect this across this midline, you're going to get this 90 degrees. And that's why you're going to have these it's nice reflection kind of a thing. That's the intuitive way to think about it. But that's okay. So we get MPK. Yes, so we can compute MTK. And that turns out to be equal to MTF, which is just equal to ADB, because again, parallel
ED.
things. Yeah. So let me write this down. So this angle is equal to this angle is equal to this angle. But I don't think MNK is very computable. How do we compute MNK?
Perhaps you could compute MNT and MKT.
No, we have MTK, we can also find TMK, right?
No, like we are assuming that MKTN is cyclic. So MNT is just 180 minus MKT, no?
No, we're not assuming it's
No,
cyclic.
you're not assuming. We want to show it is.
So what are we assuming the point N to be?
And we have assumed it to be the midpoint of CD.
Okay.
Right. So we have this. And particular angle do we have? Yeah, similarly, we also have angle KMT. That is just equal to this angle.
DF, right?
Yes, the how do we show that it's how do we show that this is cycle?
Wait, is this claim correct though? I'm just curious.
Yeah, I think it is correct.
Can you repeat which quadrilateral do you want to prove cyclic?
We have that circle MKT is since M is the midpoint of EF and T is the midpoint of DF, and K is the foot of the altitude from F to ED, the circle MKT is the 9-point circle of EFT or DEF. Yeah.
So, we haven't looked at what the 9-point circle is like.
So in order to which angle are we trying to compute now?
I am not sure. So we're just trying to see what angles we can compute in within the descriptions that we have. So anything that involves both M and N is to compute.
So perhaps we can we can compute TNS if it works, if it helps. So TNS is just 180 minus BDC and minus ACD. Yeah, BDC ACD. 180 minus BCD minus ACD.
Computing TNS. Yes, this is that is just going to be equal to this angle because of the midpoint stuff.
Yeah.
But I'm not sure how that will help. I'm not sure how it works. Let us try to see what is there anything else that we can compute.
Like we can just say that ELFK is cyclic if it helps.
Then maybe we can try to introduce some more points here. Like for
Yeah.
example,
I
Yeah,
was thinking
is
of
a
introducing the
isosceles.
midpoint of ED
right.
because we already have the 9-point circle, and then that will give us one more midpoint, which is already on the circle.
Right.
Now it should be doable because that midpoint and n we have, so like everything's midpoints now. We want to prove.
Yeah. That is true.
MKF is isosceles.
MKF is isosceles. That is true, yes. Because MK is equal to MF. I think this is quite important because we sort of over time, but I will mention this. That's just since we're mentioning this a lot. We do 9 points of it. And okay, I see the finish, I think. I see the finish. Okay, this is slightly harder problems. It's all right. But let's try to complete it in the next 5 minutes. So what is the 9-point circle? So okay, as we saw, we can consider these midpoints. Let's say MB, MC. No, we already used that. M1, M2, M3. This is not.
Okay, I also think I have.
M2, M3. So as we can see in this diagram, this is equal to this is equal to this is equal to this is equal to this. This is 90 and these are the midpoints. So we get that this is A and so this must also be A. But in fact, we know another point which is also A. If we consider this third midpoint M1, we know that it forms a parallelogram by midpoint theorem. This is parallel to this is parallel to this. This angle is in fact also A. So we get that M1, M2, M3, and B lie on the same circle. And that is very useful because by symmetry we can consider this perpendicular, we call it E, and M1, M2, M3, and E will also lie on the same circle. So in fact, we get this very nice conclusion that the three midpoints, M1, M2, M3, and the 3 feet of altitude, BEF, at Cyclic. That is quite neat. In fact, maybe I will leave it as an exercise. It's not too hard as well. You already have these 6 points on the circle. There are 3 more points that we get to also be on that circle. This is H, the Orthocenter. Again, this is like one of the school facts that blew my mind when I first saw them. So ABC, M1, M2, M3. If you consider this midpoint of AH, this midpoint of BH, and this midpoint of CH, they also lie on this circle of M1, M2, M3, BE. That is not too hard to angle save as well. So now you have, now let's call these points something P, Q, R. So you have 9 points lying on one circle. This is one problem set. So the PQR and circle is you get these 9 points lying on the same circle. So that's why it's called. So people were like, let's be very creative. There are 9 points lying on a circle. What do we call this circle? Call it the 9-point circle. Damn. So that's called a 9-point circle. And it's very useful because it passes through a lot of points and okay. So in fact, we know some more things over here. We know that this angle is equal to this. Notice that we are yet to use cyclic. I think we are quite over time, so maybe I'll try to give some more hints to finish it off.
Okay.
We have not used the cyclic condition yet. So we know that this angle is equal to this angle.
Is the construction of the midpoint of ED useful?
Maybe. Yes, it is.
Yeah, it is. I have the finish,
Yeah.
but okay, I think I'll give it to somebody else too.
You got the finish, Nisha?
Yes.
Yes, I think I'll leave it to somebody else to discover it.
Yeah, I get some good angles with it. Like PTM is equal to PDF is equal to ADB is equal to ACB
Sorry?
by the cyclicity.
So let's call this midpoint also something.
Yeah, I used P. Did we
Okay.
use P already?
No,
I
no.
don't think so.
Okay, now you have that
Yeah.
P,
So
M,
maybe I'll just
P.
try to recap till then. So now what we are trying to show, we will try to show that MP, we already know that MP, KT lie on the same circle. You will want to show that N lies on the circle with M, P, and T.
So
This
this
is
will
much
be
better because K was kind of weird, but now we have all midpoints. So that's nice.
Okay, I got it. Yes. Okay, this is fine. Yeah.
Yeah.
P is
So
actually quite
once you see it,
useful.
it's quite cute. Yes.
I
It's
think
quite
equivalent to proving
cutesy.
NTKP concyclic, which is easier.
Yes, yes, yes. Yeah.
M
Okay,
is the
so
odd one out here, and sadly.
Yes. Yes. Okay. I'm my bad. Yes.
okay,
That's
so
because you
like
can
it's
compute this angle right here. P and
yeah,
with
and then you have stuff like PM, TD is a parallelogram. So you have PM, PTM is no, sorry, P TMP is equal to TDP, which is equal to PDF, and PDF is equal to ADB, which is equal to ACB, and then you can use parallel lines to finish.
Wait, what? My proof
I'm
is
not
not.
sure how you I'm not sure how you used K here because I did not
Uh,
use K here.
no,
Nishant.
Okay, should I say it now?
I think we can just sort of leave it here maybe. I don't know if we should spoil it or something. Let me think. That's okay. Okay. I also want to just make sure everybody's following. So I think people were quite confused. This is quite a complicated problem, at least at a
This
beginner's level.
diagram is a game.
And the diagram is not the best.
Not your
So
diagram. I
okay.
meant like drawing the diagram is a pain.
Okay, okay. Thank you for defending my diagram. I shall remember this. But okay, but first of all, like people who were speaking earlier and went quiet, like Iman and Asutosh, do you guys understand this is more important than the problem, the 9-point circle?
Yeah, I understand 9-point circle, but don't understand the problem.
Okay, okay, that's all right. What about others? Is everybody on the same page with the 9-point circle?
I didn't
Saee
hear
Didi
it because I
is.
still
Mhm.
believe that it's solvable using just angle chase.
It is indeed. Have faith.
I think there are
So,
like solutions without angles here as well. Probably some projective stuff to a person who did not notice the thing.
how would
Fine.
you do projective here?
probably.
Integral
Let's
problem.
not get into
Okay,
that.
okay,
I don't
let's not
want
get
to. I
into it.
don't want to. Maybe not right now. Maybe
Yes,
at
yes,
the
yes.
end.
Yeah, yeah,
Okay.
sure.
Yeah. Okay. So, all right. So I'll just spell out the ideas and leave the rest because it's a quite a good exercise. So the idea here is okay. Let me make another diagram. So okay, this problem was kind of too hard for the class to begin with. So I already gave the hint that this point that we want to show has to be the midpoint of CD. So now all we want to show is that the midpoint of CD lies on both the circles. So I will attempt to make another beautiful-ish diagram. Cat. Okay.
Hello,
A,
I'm
B,
audible.
C, D. You are Sanskar. You are not audible.
Yeah,
I can hear you.
yeah.
Okay.
Actually, you were lagging for me, so I couldn't get what you were saying. I was asking if I could like solve the problems and DM you the like solutions. Would you mind?
You can
checking?
DM on, I would not mind checking them. You can also put them on check my solution, please. And somebody, and just like make sure to spoiler them. So you'll actually get a much, oh no, the lights have went off. You'll
Okay.
get a much faster response. But I don't mind you DMing me as well. That's also fine. Whatever you're more comfortable with.
Okay, I'll do this.
So we have this, and then we consider, so we have a bunch of midpoints, a bunch of feet of altitude. So now you consider the 9-point circle in EFD. So that is going to contain this midpoint M, this midpoint T, and this feet of altitude K. And that is nice for us because MKT is a circle we are interested in. We want to show it passes through N, which is this midpoint. But this feet of altitude is slightly scuffed. So the way we eliminate that is by adding another midpoint which is there on the circle. So we know that since the 9-point circle passes through all the midpoints of the three sides, we add this midpoint as well. We call it P. And now we know that circles MKT and circle MPT is the same. Why? Because of 9-point circle in EFD. Okay, and then you can look at circle MPT instead of MKT. You can eliminate K, and angles are usually very, very nice with just midpoints. And now you want to show that M, P, T, and N are cyclic. Now you can try to show that. That is very nicely angle feasible.
I mean, there is a finish through K, but yeah.
Yeah, there is a finish through K as well. I found this one more intuitive. Maybe we can discuss that. Okay, I'll try switching on my camera. Yes. All right. I think we are already 20 minutes past the time. If there are any questions about the main things that we discussed, okay, the problem finish, you should try it on your own, and if you don't get it, feel free to ping me like 5-6 times. No, don't ping me 5-6 times. Maybe 3 times if I don't reply the first 2. And I wouldn't mind helping you out. And yes, I mean you're free to leave at any point during the class. I'm not keeping you here. I think I'll just stop the recording if there are no more questions about the things that we discussed.